liquid level, and indeed this film should be called level, because in some cases we also measure the level of a tank containing solids, like for example grains or pellets or cement, sand, whatever. And this first film is about hydrostatic gauges. Hydrostatic gauges are those that depend on one simple equation, rho g h. The pressure is rho g h. And rho is the density of the material, g is the acceleration, the gravity acceleration, and h is the height of the liquid. And this h is what we really seek to find. But in those cases, the density is a part of the equation, so we need to calibrate that for the liquid or the contents of the tank. First of all, the Displacer Gauge is a device where you have some kind of a rod into the tank, like this green rod in this figure here. The buoyancy in Norwegian oppdrift of that rod depends on how much of the rod that is soaked into the liquid. So the force that I measure on top here depends on two things. The gravity, the gravity will try to pull the rod downwards, and the buoyancy will try to lift the rod upwards again. So as the more liquid that is in the tank, the more buoyancy you get to the rod, and the lighter it becomes, and therefore the force that I measure here on top becomes less and less and less as I fill the tank here. Therefore, and the buoyancy, the force that I measure is a function of the gravity and the buoyancy. And the buoyancy is the volume that I soaked multiplied by the density multiplied by g. And the volume is, of course, area multiplied by the height multiplied by rho multiplied by g. The area is the cross-sectional area of the rod itself. And therefore, the measured is a function of the height. Since the buoyancy is a function of the height, then the entire force is also a function of the height of the liquid. A bubbler, on the other hand, is a device where you have a gas supply, and that gas supply is used to press bubbles out of a pipe soaked in the tank. When you have a pipe that is soaked in the tank like this, liquid level here, well, with no pressure, the liquid will also be inside the pipe. When I apply a pressure here, I have to press the liquid out of the pipe first before bubbles can form out of the pipe. So the higher the column is inside the pipe, the more pressure I'll have to apply in order to get bubbles out. Once the bubbles have started to form on the outside of the pipe, well, that sets the maximum pressure that I need. So the pressure applied here will not overshoot the pressure required to push bubbles out of the rod. So therefore, if I have a pressure sensor here, I can measure the pressure that I have to apply from the gas supply in order to get bubbles out of the rod. It's a simple design and it's cost effective, and more than that, it's ideal for level measurements where we have debris, foam, steam, surface turbulence, and other things that makes other measurement principles difficult to apply. A third method that uses the rho GH relation, the pressure relation, is to have a differential pressure meter. So in this case here, I measure the difference of the pressure on top of the tank and at the very bottom. And the pressure here is rho GH. And maybe I have a pressure in this tank as well, that you have, for example, compressed air, since the tank here, there is no opening in the tank. So I have a pressure there as well. In this case, exactly the same, but the tank is open to the surface, and hence the pressure meter is also open to the outside atmosphere. In the first case here, the pressure, it depends on rho GH alone, while in this case the pressure depends on rho GH plus the pressure of the gas above it. But then I measure the pressure of the gas above it, and I can differentiate that from the total equation, and I end up with rho GH alone again. So again, the delta P, which is what I measure, is a function of the liquid height.